Sticking with our discussion of geography as a science and taking a science perspective, we come into physical geography thinking about a systems approach to the planet Earth. Specifically, we consider Earth to have four major systems: the atmosphere, all the air that we breathe, which will be the highlight of this semester. We'll also dive into the water on planet Earth, which is the hydrosphere. And then in part two of this two-part sequence of physical geography, you dive more so into the biosphere, the life on the planet, and the lithosphere, also referred to as the geosphere in our textbook, as the rocky planet that is also active. Every year our continents are moving, new islands are forming around the world. In the last several decades, we've had several new islands emerge from the ocean floor through volcanism, and at the same time, mountains are slowly wearing down. When we think about systems, they're as large as the planet itself is one big system involving all four of those parts we just looked at. You can break it down to a smaller scale, or isolating things like the atmosphere, or you can isolate even to a smaller scale, maybe the size of a river, or a tree, one single tree, instead of the entire forest ecosystem. Or you can get down to a leaf on a tree. So there's a variety of scales of systems, and it's a matter of finding the one that's the most practical. And regardless of the scale of the system, we can consider it to either be an open system or a closed system. On the planet, most studies in physical geography examine things that are considered open systems, such as the stream we see on the top image. Open systems allow for energy and matter inputs and energy and matter outputs, where closed systems only have energy inputs and outputs, and the matter is contained. So the planet Earth is probably our best example of a closed system where all the matter, all the things of substance, the air, the water, the soil, the rocks, the people, the penguins, everything that we consider to be matter, soil, it's all contained to the planet itself. We don't lose things to outer space. I mean, there are very insignificant examples of hydrogen atoms at the very top of our atmosphere slowly leaving the planet. And they're very, very limited, or at least very limited significance of matter coming into our planet, but every day we do get bombarded by space dust. But for the most part, what we like to do is to think of the planet as a closed system and say all the matter is contained within the planet, not getting regular imports of water, let's say, from comets on a daily basis, or losing our water to outer space. The water we have has been here for at least 3 billion years and in the same quantity. Where when we look at a more practical scale, something like a stream, it does allow for matter inputs and outputs. Water can enter into the stream and exit the stream. Plants can drop their leaves into it. Fish can procreate. Frogs and amphibians can jump into or out of it, and so forth. So matter can go in and out. Energy, pretty much what we're considering with energy is sunlight. There are some other forms of energy coming from the Earth's interior, such as plate movement, but the energy we will be considering this semester all comes from the sun, that star 93 million miles away from us. A neat thing about Earth's natural systems are that they tend to be in equilibrium, which means balance. And if we think about equilibrium, having a balance in a system, it can come in two forms. It can come as a stasis or a static equilibrium, where the system has virtually no change at all over time. Or what we tend to find in the natural world is what we call a dynamic equilibrium. If you think of a lake level, let's say, over time it hovers around the same lake level, how deep it is. But sometimes after a lot of rain it might spike and be higher and flood some of the lake coast, and other times during droughts it might dip low, exposing some of the lake bed. But over time, with the rises and falls, it hovers around this average lake level. And we find most Earth systems hover around a dynamic equilibrium, which is a good thing. Otherwise, we would be surrounded by chaos. So here's our example of a lake, which is actually a reservoir, artificial lake. You could, if you're studying this lake, you would want to analyze all the different inputs and outputs, the evaporation versus the precipitation, the runoff from streams, how much is controlled by, maybe it's the Army Corps of Engineers allowing water to exit, or maybe it's Alabama Power allowing water to exit, and so forth. And you can see over time the lake level is going to be constantly changing, but it would still be recognizable to anybody who's familiar with it day after day, season after season. Here's a glacier. In the high mountains around the world, we find these permanent masses of ice that actually have a flow component to them. They slowly kind of work their way down from higher elevations to lower elevations and carve out massive amounts of rock in the mountaintops. But throughout the year, even though they're permanent fixtures in the mountains, they do recess and grow with the changing of the seasons. But year after year, you should find these glacial systems being a balance or a dynamic equilibrium. And one of the things that climate scientists are doing today that's reassuring the hypothesis of global warming is that we are seeing the ice recessing year after year. And when it grows in the wintertime, it's not growing to its fullest extent it had in previous years and previous decades. We're finding an overwhelming majority, in the 90% of, I forget the specific percentage, but somewhere in the 90s of all glaciers on the planet are receding from where they have been in the earlier parts of the 1900s. Within systems, we also have feedback loops. Feedback loops come in two forms, negative feedback loop and positive feedback loop. And it's kind of counterintuitive. The negative feedback loop is the feedback loop that we like to see. We like to see these types of feedback loops in our Earth systems because negative feedback loops keep the system in balance or equilibrium. A positive feedback loop is a feedback loop that takes a system away from balance, either in an increase of a certain variable or a decrease of that variable. If it's lake levels, it would be something that would continue the lake level to get shallower and shallower and shallower and shallower instead of some type of trigger that would cause it to increase again and go back towards its equilibrium, like a negative feedback would do. Some very simple examples of these. The first would be your bank account. If you put money into your bank account, it accrues more interest. And as that interest accrues, it allows your bank account to grow. The principal amount then grows, and then the interest on that grows, and then it grows, and so forth. So that would be one example of a good type of positive feedback loop where the money in your account continues to grow away from a balance. But in natural systems, that's usually not a good thing. In your bank account, sure. Your human body temperature is very finely tuned. If you get a little bit, let's see here, if your body temperature starts to rise just a little bit, your body responds by sweating, perspiring, and that's a cooling mechanism which causes your body temperature to drop back down. So here we started with temperature rising, results with temperature falling. That keeps us in balance. That would be a negative feedback loop. A threshold is reached, and that's a good vocabulary term. Threshold is a tipping point. At some point there will be a massive change in the system. So let's start by thinking about a positive feedback loop in the climate system. Let's say that conditions were getting colder. So year after year we're finding a global, this is not the case, but let's say it was the case that the global average temperature was getting colder. That would allow for more ice accumulation at our north and south pole, and our ice caps would start to grow over time. So one of the feedback mechanisms would be, well, with more ice growing, that means that the Earth can reflect more sunlight. And if it's reflecting sunlight, that means the Earth is going to get colder. The opposite would be to absorb sunlight, and that would make us warmer. But as we get colder, one of the responses in the system is for more ice accumulation. And that causes more reflection of sunlight. And that ultimately leads to Earth getting colder still. So that is what we mean by positive feedback. You're going away from balance. So we started at a temperature, we got colder, and the response was to get colder still because of the ice growth is one of the mechanisms. Eventually, Earth could get so cold that a threshold is reached where now the atmosphere is so cold that evaporation ceases. So without evaporation, you can't have snowfall, and you can't have your ice caps getting any larger than they are at that point in time. So perhaps then after that threshold is reached, the ice is given the opportunity to melt and get slightly smaller, and then you might find that a positive feedback mechanism could go and work in the opposite direction now. Whereas the ice gets smaller, the Earth can absorb more radiation and allow the ice to shrink even more, which would cause the Earth to get warmer because more absorption would be taking place now instead of reflection, and you would continue in the opposite direction.